In this video, I'm going to walk through a simple ball screw sizing example using the Sigma Select software. Hi, I am Micah Studeman. Here's a quick preview. We're going to walk through sizing a ball screw for a simple milling machine. The ball screw specifications and motion profiles have been defined and can be loaded into the Sigma Select software to find the best motor for this application. Now let's take a look at this in a little more detail. At this point, I assume that you have watched the following videos that introduce you to the sizing concepts and software. Here's a visual representation of a simple milling machine. The machine consists of a rotary milling head, vertical adjustment actuator, and a linear ball screw. The part is initially loaded onto the ball screw and then lined up for milling the first slot. The rotary milling head moves down into the part, and the ball screw moves to the right slowly to cut the first slot. The milling head then lifts out of the part, and the ball screw positions the part for the next slot. The second slot is drilled just like the first, and then the part is lifted off the machine, and a new part is put on. The finished part consists of 2 milled slots, one on each end. So what size of motor is required for the linear ball screw? The load characteristics and motion profile for this axis are both important. The following specifications have been obtained for sizing the ball screw motor only. The vertical motion and rotary drilling motion are not being sized within this video. Looking at the linear ball screw, it consists of a 20 kilogram slide assembly, which includes a jig to hold the part to the ball screw. The metal part being cut has an overall mass of 60 kilograms. The screw itself is 1200 millimeters long and 20 millimeters in diameter with a 20 millimeter lead. The motion profile can be split into 7 sections. 3 of these sections are dwell sections to allow the mill to move into or out of the part. 2 of the sections consist of cutting 3-inch slots into the material. 1 section traverses the bit from the first slot to the second slot. The last section is a dwell to allow the part to be removed. Looking at the 2 cutting sections, the ball screw needs to apply a constant cutting force of 700 pounds onto the material, which in turn means that the screw cannot move faster than 1 inch per second. Moving faster could result in breaking the milling bit. During the traverse section, the ball screw can move at 20 inches per second. Let's start sizing the motor by opening the Sigma Select software. For this example, I will be using version 1.0.8.3. To start, I have already filled out the user information section. In the Load Editor tab, we can start filling in some required information. First of all, what mechanism are we trying to size the motor for? In this case, it will be the ball screw portion of the milling machine. So I will select the ball screw icon from the left side. Let's look into some of the load info. First in this section is load mass. What should be entered here? Well, looking at the application information, I see the ball screw has a 20 kilogram slide that is moving a 60 kilogram piece of metal. So I will put the 60 kilogram mass in because that is the load. Moving down, let's consider what external forces may be present. This load does have external forces, but looking at the help file, the external forces on the ball screw are not constant. The cutting force only occurs when the bit is cutting the metal part. So this cutting force is not recognized here, but will be added when it comes to creating the motion profile. When it comes to friction force, we are looking for items in between the load and the mechanism that may cause constant resistance depending on the load. In the ball screw, there is a friction force occurring in the linear guide portion of the ball screw due to the slide bearings. This force is added by selecting the friction coefficient calculator and selecting linear guide with 9-line bushing under the mechanism menu. Since the ball screw is mounted horizontally, we don't have to worry about setting the inclination. Now that the load is defined, the next step is to fill in the mechanism properties, which are defined by the mechanism type that was selected earlier. The ball screw lead is the translation value for the ball screw to turn rotary motion into linear motion. In this case, the screw lead from the spec sheet is 20 millimeters. The slide mass is just the mass of the slide moving on the screw, which is 20 kilograms. Now for the ball screw inertia. If you remember from the servo sizing basic concept video, the moment of inertia is a measurement of how difficult it is to change the rotating velocity of the object. In this scenario, we're looking for the inertia of the ball screw, which is the rotating part of the mechanism. The specification from before does not list the inertia directly, but we know the material and dimensions. These can be used in the Inertia Calculator. The Inertia Calculator takes a user-defined model of the screw and calculates the inertia of the defined models. In this case, the screw is the only component that needs to be added. I'll set the label to screw and set the type to cylinder. There's only one screw in the actuator, so the quantity will be 1, and there are no transmission components being used, so that will stay at the default also. Looking at the diagram, the screw needs to be modeled in the vertical orientation. From the ball screw specs, the length is 1200 millimeters, so the height is 1200 millimeters. Normally ball screws are not hollow, so the inner diameter is 0. The outer diameter from the spec sheet is 20 millimeters. The offset is 0 because the screw is rotating around its own axis. Predefined materials are available from the material drop-down. This ball screw is made out of stainless steel. If the materials are not available in the drop-down list, the density and mass can be defined by the user. The inertia for the ball screw has now been found. Moving on, the normal efficiency of the ball screw can be seen by selecting the Info button. According to the chart, ball screw mechanisms can be 85 to 95% efficient. The manufacturer may publish a more precise value, but this is usually sufficient for sizing purposes. So I will use 90% for my efficiency. The ball screw is connected to the motor via a coupling, which needs to be added in the transmission section. To start, let's select the calculator icon. Inside, we are going to add a coupling, and then set the inertia for the coupling. The coupling that will be used is 60 millimeters in length, and 38 millimeters for an outer diameter. The inner diameter is 20 millimeters to match the ball screw diameter. The inertia has been found for the coupling. Let's move on to the profile editor. Now we need to move the information from the Move Profile, shown earlier, into the Profile editor. To make sure that the correct units are used, I need to set the unit options to inches, seconds, and pound force. The first section is a dwell for 0.5 seconds. Then comes the first slot, which will be a trapezoidal move. This cut is 3 inches long, and the screw can travel no faster than 1 inch per second. Here's where we need to put the external cutting force. It needs to be negative because it is acting against the ball screw. Next we have another dwell for the bit to come out of the part. Then the transfer move, which is going to be a triangular move over 20 inches at 20 inches per second. Another dwell for 0.5 seconds. Then the second slot, which is just like the first one. So 3 inches at 1 inch per second with negative 700 pound force. The last section then is the extended dwell for bit removal and part removal. Let's make this 10 seconds. Now that the motion profile is finished, a motor can be selected from the motor results page. When selecting a motor, the following 4 key sizing factors need to be taken into account: inertia ratio, speed, max torque at speed, and RMS torque at speed. For this application, let's use the Sigma 7 non-gear motor. Looking at the non-gear motors in the list, I want to find a motor that satisfies all 4 of the key sizing factors. The SGM 7A-25A motor fulfills all 4 of the key sizing factors, but a rule of thumb to use when sizing is to make sure that the required torque does not exceed 80% of the rated and peak torque values. This allows a buffer if the customer specifications are a little off. The SGM 7A-38 motor appears to have rated and peak torque values 20% above the required torque. so let's select the SGM7A-30A motor. Other secondary factors also need to be considered, like cost. Sorting the list by cost, it appears that the SGM7G-20A motor is cheaper to buy and still fulfills the key factors. Let's select both motors for right now. In the motor detail screen, I will look at the SGM7G-20A motor first. Looking at the speed/torque graph, the RMS torque value lies in the continuous region, and the peak torque lies in the intermittent region. This satisfies 3 out of the 4 key sizing factors. Looking at the motor detail area, the inertia ratio falls underneath the allowed inertia ratio of the servo motor. If you remember from the previous sizing videos, the lower the inertia ratio, the better the motor will be able to control the load. So this motor's inertia ratio satisfies the last key factor. How is the SGM7A-30A motor different? First of all, it has a max speed of 6,000 RPM and a rated speed of 3,000 RPM, because it is an A motor versus a G motor. The inertia ratio for both motors is low, so this is not a concern. Because the application operates at a lower speed, the high speed characteristic of the A motor is not required. But if the ball screw lead is decreased to 5 millimeters, and the profile is adjusted just a little bit, a high-speed motor could be more practical. For right now though, let's choose the SGM7G-20A motor and use the requested ball screw size. The regeneration tab shows an external resistor is not needed because no negative torque is being produced for this application. Thus, no regen energy is being created. The sizing is now complete and a sizing report can be created. The report contains all of the information that was used to size the motor along with the motor specs of the selected motor. The SGM7G-20A motor will work for running the linear ball screw of the multi-axis milling machine. This concludes the ball screw sizing application. For more information on Sigma Select and motor sizing, visit yaskawa.com.